Hello, everybody, and a very good morning, good afternoon, and good evening, and a very warm welcome to all of you who are attending this online webinar from all over the world. This event is being brought to you live by the Institute of Marine Engineering, Science and Technology, Houston Gulf Coast branch. I'm Rajneesh Kelkar, the Vice Chair of this branch. Please note, this webinar is view and listen only mode. Therefore, please use the Q&A chat box in Slido to submit your questions. These will be addressed at the end of the presentation by the speaker. You will have received the link to the Slido Q&A chat box from the Eventbrite invitation when you registered for the event. Well, today I'm delighted to introduce to you a very distinguished speaker, Mr. Subrat Nanda. Subrat is the Chief Data Scientist at the American Bureau of Shipping in Houston. At ABS, he leads the data science and advanced analytics efforts. And today he'll be talking about building successful artificial intelligence-based products and services for the marine and offshore industry. He will also touch upon the challenges faced in building these systems and also share a few lessons learned. Subrat has more than 20 years experience in applying artificial intelligence to industrial problems in areas of condition-based maintenance, prognostics, diagnostics, and health management of equipment, in reliability engineering, statistical risk assessment, and performance enhancement. He has successfully developed and deployed over 100 applications using machine learning, artificial intelligence, and data science in diverse domains such as marine, offshore drilling, gas turbines, wind turbines, financial risk, inspections, and even marketing. Subrat holds a master's degree from the University of Exeter in England in autonomous systems and a bachelor's degree in engineering from the University of Nagpur, India. He has filed 15 US patents, holds 6 trade secrets, and has authored more than 40 publications in this area. We are very fortunate to have Subrat here with us today. So with that, let me now hand over to Subrat to make his presentation. Subrat, over to you.
Thank you, Rajneesh. Good morning, everybody. Good afternoon, depending on where you are globally. So as Rajneesh mentioned, we'll spend the next few minutes talking about some lessons learned in the industry when working with real industrial data and problems and using artificial intelligence and the challenges we saw. So let me know if you guys can see my screen and I'll begin the presentation. Okay. So this is just an overview of what we'll talk about. We'll start about, why do we use AI and ML, the different kinds, roles, and importance of data. How do you handle issues with data quality? As you might be aware, especially in the real world, data does not come served on a platter, right? There's always data quality challenges, whether it is sensor data or whether it is discrete and transactional data. So we'll talk about those. And I'll give you some insights into how we have tackled those problems. We'll then move on to the topic of condition-based maintenance, which will be, my aim here is to dispel a few myths of what CBM is and what it isn't. We'll also talk earlier in the presentation on similarly on what is AI and what probably it is not. So we have some common baseline definitions. Again, the caveat here is these definitions are based on applications in the industrial world. So we'll talk about more when we come there. Then I'll give some examples of how condition-based maintenance can be done, different kinds of strategies to do it, and some examples. Before moving on to the also important topic of digital twins. These days there are so many definitions and use cases of digital twins, but what does that mean in our industrial world, right? When you talk about dealing with assets such as engines and turbines and propulsion systems and engine systems and drilling operations and so on. So what does it mean in the heavy metal asset world? Then I'll share some key lessons that we have learned when we're trying to apply these technologies and implement them and field them, more importantly, into the real industrial world. So with that, I'll start. As we start this, before this, I want to give you a quick introduction to who is ABS. So ABS, as you probably are aware, is one of the world's leading maritime organizations for classification in the marine domain. We are the society for the United States, and with offices in about 200 countries and 70 countries and 200 offices. We provide traditional classification services as well as technical services. So, anything from new construction to engineering design reviews and survey after constructions, all the way to energy efficiency and life cycle management, and now even in the digital world. So this is a quick overview of my own journey into the world of applying digital technologies to the industrial world. I won't read everything here, but very quickly, I just want you to tell a couple of things here. I've been in the field for about 20 years. So I've been a practitioner of applied CBM, PHM, reliability, statistical analysis to, as you can see in the pictures here, all industrial heavy assets, especially in the areas of how do you combine the domain knowledge and the physics of these equipment with AI, machine learning, and prognostics and statistics and risk management. Outside of my work, I love to do various things like teaching math and so on. Okay. So how do we apply machine learning? What's the overview? Like, there's so much talk and so much of applications that you might be hearing about fielded AI systems. So to make it very simple, I have actually condensed it into a schema here. And the way I would like you to see this is from bottoms up. So at the bottom, and we'll discuss all of these elements over the course of this discussion, but this will give you an overview. So at the bottom is different kinds of data that is collected, right? So you have information from commercial data being collected, operations data, which is sensors and repairs and services. You have data around your vessel performance, emissions. If it's a moving asset, then even lat-long information, meteorological information, and so on. And then there's a lot of data which is of transactional nature, right? Your inspection reports, vibration analysis, which are not done on a continuous basis, but at discrete points in time, right? Your CMMS systems, which are mostly looking after repair and maintenance logging information. And then there's data looking into how different products move, different parts and spares are being stored and recorded, which inventory did it come from, where did it get installed, and so on. So these are, and of course, I'll have some more slides on all the other kinds of data, but the whole idea is the underlying foundation of successful machine learning and any applications that we are talking about in the digital world solidly rest on diverse and good quality of information and data. And of course, quality there is relative, right? So we'll talk about data quality. Then is the layer where in the middle, in the gray here, where I'm pointing now, is the fundamental capabilities that we need to build, or which we have built in our case, which basically derive on this data. So things like predictive maintenance, right? It's a very broad and deep at the same time topic, right? What does it mean to do predictive maintenance? Anomaly detection. What's the definition of an anomaly? What do you do once you get an anomaly? How does that relate to predictive life? What kind of actions can you take, disposition, process, and so on? And then spares optimization, a big problem because what kind of spares were used? Were these of the same type as the part that is being replaced? Did you change? Did you put in a new spare? Or was it like a used spare and so on? And which inventory did it come from? Where did it go? The whole problem in optimization here is answering specific questions on what parts to keep, where to keep, and then from where to draw them. And then condition-based maintenance is another topic I'll talk about, which is another fundamental capability that we have to build, built on the foundation of data. And of course, domain knowledge is condition-based maintenance. So what does it mean to do condition assessment and then maintenance management? So I'll talk about this definition when we come there. And of course, the end goal is what you're in our industry or in every industry is what the leadership's goal is, which is reduction of OpEx. If I can reduce the unplanned failures and move them to a planned scope, it reduces a lot of operation expenditure, right? Similarly, if I can improve, first of all, can I even assess the performance and productivity of my assets and of my personnel? Can I identify opportunities for improvement in people, product, or processes? Fleet efficiency, as it's aware, is about efficiency, enhancement in the routes that our ships take, or the rate at which we derate them, and so on, emissions and so on, and fuel efficiency. Reliability, availability, and maintainability. Actually, we'll dig a little deeper into this one as well, where we'll talk about how do you assess reliability and availability, more importantly, to take fundamental decisions regarding resource allocation to improvement of reliability. To be able to answer such questions, you would need to talk about, well, what is my baseline reliability today? How does my asset compare to the rest of the fleet? What parts of my assets have reliability entitlement, high reliability entitlement issues? And what must I do in order to improve the reliability to derive the maximum return on investment? We'll answer some of these questions and look at some methods there. And then, of course, all of this leads to growth of revenue, because if my vessel is more reliable and highly reliable, or if my rig is highly efficient, my processes are taken care of, I can actually now go and fight for more revenue, or I can probably offer new services, right? So these are the kind of decisions that we have seen being applied for using AI and machine learning methods. So let's start with what is AI and what it is not, right? So there's so many definitions you must be inundated with. In my view, I have a simple definition of what AI means for us in the industrial world. It simply refers to computer systems or algorithms which learn patterns from data. They adapt and evolve as new data patterns emerge, and then they have the capability to continue to perform the learned tasks or whatever patterns they have learned as data refreshes or as new data arrives. So if you see, this definition has three basic parts, which I think is more directly applicable to our use cases. One, can we learn some patterns from data so I don't have to program it explicitly? Does it have the capability to adapt as new information arrives, or as newer data patterns emerge, or at least tell me that it is no longer working with the same set of assumptions as it was built upon? And then can it perform whatever it's supposed to do, take a decision, detect an anomaly, or root cause a issue, or predict a failure as newer data arrives with certain degree of confidence, right? So these are three basic parts of that one-line definition. And in that vein, what I've seen is there's a lot of myth, right? So AI does not stop bad things from happening. It can reduce the impact or give you proactive alert time so that you can take corrective actions, or proactive actions, I should say, for failures, attrition, degradation of performance, and so on. So it is about management of knowledge, understanding the condition of your equipment, asset, rig, vessel, engine, pump, whatever you work upon. It is a decision support system. It is not going to replace the human. It is the function of AI algorithms is simply to be a decision aid. It's like a tool. And then, of course, it can help with prediction of events and so on, and identify changes in customer behavior. So what this means is, let us say we place an equipment for a certain intended operation type. Let's say you have a diesel engine or a turbine, which is supposed to assume to be working at a base load operation. What if, due to the economics of the type of trips that they're taking, or the economy that they're performing in, they change it to a peaker type operation? So now suddenly all your assumptions that you had when designing the equipment are no longer valid, just because of change in the customer behavior. That, of course, has impact on the type of failures, on the type of equipment degradation, and the type of spares and design upgrades you will need to think about. So that is what I mean by customer behavior. And then, of course, at the heart of it is, how do you identify these patterns, right? So this is all these are the types of questions that artificial intelligence can solve for you. And these are the types of myths that you need to be aware of, right? So it's not a silver bullet. It's not a bullet at all. Okay, so let's start with what is data. So when I started looking at multiple industries, and I showed you in my previous experience, applying artificial intelligence to gas turbines, wind turbines, aircraft engines, aeroderivative engines, and marketing applications, and marine applications, and deep sea drilling, offshore drilling. Data comes, there are several stages during the asset life cycle that data gets generated, right? You have a lot of data that is being generated when the product is being designed or being manufactured. Testing information, manufacturing information, engineering design data. OEMs may give you their own reliability, burn-in testing data information, and so on. Once you move to asset usage for operations, there is different kinds of data that gets generated. You're no longer in a lab environment. So now you will have sensors collecting data in a noisy, ambient conditions can be extreme. Failures will happen. So you will now start moving into asset services. You will repair them, you will inspect them periodically, class will get involved. So there's a lot of data that the societies like classification societies like us will collect. There will be annual surveys, there'll be 5-year surveys, and so on. And then you will have information how the asset is interacting with its own operation, right? So your customer or your asset will be, sent for dry docks. You will have integration with other systems, and that will give rise to more information and data. And then, of course, over the life cycle, you will continue to maintain it, right? And at the end of it, at some point, you will decommission. So all of this asset, this life cycle of an asset will generate multiple types, multiple frequencies of information. Before I leave this slide, think about it. All of this data is not the same type, right? Some of it is nicely structured and time series sensor information. Some of it is highly disorganized textual information, like the ones that you collect in your maintenance records, or images that you may collect to look for corrosion, or maybe oil monitoring and vibration monitoring, where for a very short period of time you will expose your asset to very high resolution data collection techniques and so on. So all of this data is not the same. So the challenge is, how do you even begin to wrap your heads around this multiple types of data and then make decisions as to how to use it? So what I did was, the first thing was to kind of arrange this information in a format that we can try to put our heads around. Because the important challenge is to be able to fuse that data to derive insights. Otherwise, you'll be working with silos of data, and you'll be missing on several. You will confuse correlations with causations. Here are the 6 types of data that I came up with, depending on the types of information you saw on the previous slide. So one is the types of structured operational data, where you're looking for sensor data. There'll be information regarding mapping of sensor tags. Sometimes the same sensor on different assets of the exact same type can have different names or different units of measurement. All of that information needs to be mapped. Where are these sensors mounted, and what are they measuring? Can be different. Surprisingly, I should say unsurprisingly. And then we have information which is events type, which is failure findings, warranty repairs, warranty logs of repairs, equipment taxonomies of how equipment is arranged. You will gather data with respect to in situ tests like oil and vibration and others. And then you will collect third-party information like additional data from demographics, ocean conditions, inspections done by other third parties like gaugings and corrosion, and of course class societies will collect a lot of information. And then parts consumption, right? Cost, and so on. So this is the broad category of data that we have kind of bucketized, if you will. And of course these are not set in stone. They are fluid, because we keep finding newer sources of information. At the heart of this is the idea that you cannot, that's another myth actually, that you put all this data into a big cloud computing platform and magic appears. My experience is that there are 2 schools of thought, right? At the one extreme is, I don't worry about physics or operation, just give me the data and I'll put it in some computing platform and magic appears. The other extreme school of thought is, I don't care for data, and you only rely on first principles. So what I've seen is neither of the two will give sustainable and meaningful insights. For that, you need to do a hybrid between data domain and data science, right? So if you want to solve a particular problem, you need to not only have the domain knowledge and the background information, but you have to collect the right data. Sometimes, even if it's an important problem, there's a lot of need to solve it. But if you do not have the right data collected for that, we cannot move further, right? So all 3 have to align. But in general, I've seen that when you start combining domain knowledge about the physics and operations and changes in operations with data science, meaningful results start to appear. Of course, when we talk about data, there's a huge problem of data quality. So I'm just showing one slide and I can actually do a whole 2-hour discussion regarding different types of data quality issues. But I'm only showing here the issues faced with textual information, which is mostly collected in our repair logs and maintenance logs and CMMS systems and so on. So even if we're looking for basic textual information, there's so many inconsistencies we find. I've listed a few of them here at the top left. You'll see non-standard abbreviations being used, inconsistent equipment taxonomy. So sometimes the different departments in the same company working on the same asset may have different taxonomies, or maybe especially if you're dealing with multiple vendors. So if I have engines from vendor A, B, C, the taxonomies of how their systems are classified and what comes under what parent-child relationship is completely different. So that becomes the biggest headache when you're trying to reconcile their systems. Of course, there is variation across users, human beings being a big factor, right? So if people from different parts of the world were to express the same semantics about a problem, the use of language, the construction of the sentences will be very different. But they might all be talking about the exact same condition or the exact same asset. Data, of course, is missing. It's at the end, it's humans entering the information, sometimes due to human errors and sometimes due to a genuine lack of information. For example, if I'm repairing, I may not have the right information about why it happened right away, right? So data becomes missing. Common language mistakes such as spelling errors and grammatical errors, of course, and sentiment expression variants like I talked about. So these are some of the biggest, and there are many more, but some of the top reasons for why we have seen textual data is very inconsistent. And what's my answer? So we actually spent a lot of time, and what we have now is what I'm calling now as AI for AI, which is we actually developed a whole natural language processing tool to address this challenge, so that before you can begin any meaningful data science and AI modeling, the first step is to use AI technologies to create the data so that, or to sift and clean the data and pre-process it so that it becomes amenable for more advanced modeling. So in that sense, it's basically using artificial intelligence to actually do the prep work to help us build more useful and meaningful models. And the main reason I say this is because what I've learned and seen is many times due to the lack of good information in terms of data quality, we tend to continue to over model and if I can use the word, beat the data to try to ask questions that it cannot answer. And solving data quality issues upfront, whether it is sensor information, for example, you can use imputation type methods to solve sensor quality problems. And I'll show you an example here for textual data problems. The rest of the modeling becomes a lot more straightforward, and you are less likely to cause confusion between causations, correlations. The user adaptability improves because everybody can understand how the data was improved. You will no longer be, your confidence in the models will improve, statistical confidence. So for reasons like this, I think it's best to start looking at data quality issues seriously and dedicatedly and intentionally spending modeling effort to improve those. Okay, so let's come to condition-based maintenance. So, a lot has been heard, and I keep hearing a lot of definitions. I came up with a simple definition of condition-based maintenance based on the last couple of decades of experience. I think it's a maintenance methodology. So it's not a widget, it's not a tool. It's a methodology where the intervention is performed only when the need arises. So that's a loaded equation, but basically, I think the condition-based maintenance problem consists of methods to assess the condition and methods to manage the maintenance, right? So how do you assess the condition? You have technologies like remaining useful life estimation. Can I know how much life does the equipment have before a functional failure happens? Can I diagnose why those failures will happen? And can I understand the root cause classification? What's my reliability risk? And more importantly, what's my change of reliability risk over time? Can I detect anomalies? All of these questions will simply tell me what is the condition today and or maybe extrapolated into the future. But still your answer is not, how do you maintain, what should I do? And that's the whole part of maintenance management, where we talk about, okay, spares optimization, risk-based decisions. Should I move a repair to the left? Can I pull it to the, can I push it to the right or pull it to the left? Can I wait for the next available overhaul that is being planned? Or do I need to derate a certain engine? These are risk-based decisions. What kind of spares will I need? What kind of tools and person will I need when the repair has to happen? And so on. Similarly, what is condition based? What isn't condition based is, again, it's a big myth, is it's a replacement for a human. Absolutely not. Condition based maintenance is to help and aid the human to make a more informed and repeatable and data driven decision. That's about it. CBM by itself will not fight bad data, right? It will not be able to fight human-induced errors or technical errors in the data or skepticism and so on. It is simply a tool to help you make better decisions. And another myth I see is, well, it will always will it make me move left, meaning on the bathtub curve, meaning will it always help me? In the long term, yes, but in the short term, condition-based maintenance may actually lead you to perform more maintenance, because if you're not using the equipment the way it was intended to, or maybe due to geographical conditions or fuel availability, or maintenance maturity, or rigor to and adherence to maintenance policies, if your asset is degraded in a rate at which it was not designed to, CBM method can actually expose that and give you the right inputs to be able to perform the right repairs at the right time, such that over a long period of time, yes, your OPEX, your total cost of ownership or operational availability will improve. So that's the whole idea of why these technologies exist. Okay, let me cover some of the examples of CBM. So we'll talk about anomaly detection, which is again a very widely used technology. The way we have developed this is to be able to build any anomaly detection algorithms. The first thing is, once we obtain different types of information about the asset, all the sensors and so on, we actually want to use and understand what is the detailed physics of failure of those equipment, so that we look at equipment and its failures in entirety, like I said, combining domain and data science. And then here's a quick example. What does it do? So if a failure actually happened here, can I detect some anomaly ahead of time, such that it gives me not only why the anomaly is happening, so I can plan what kind of repairs need to be done, what kind of parts will need to be procured, but also I'll have some idea of how much time I have left to make that decision, right? So suddenly the whole idea of removal of unplanned downtime is basically what anomaly detection enables for you. And of course, as ABS, we delivered this insight as an anomaly report. So we have now applied anomaly detection to over 70 hardware systems, and every algorithm. For every system, we have a dedicated set of algorithms, basically looking at the health of that equipment, where we have combined statistical anomaly detection with physical knowledge, with design of the physics, and with failure information from history. So the whole idea is not just detect failures which or conditions or anomalies which look different from how the data has operated or how the asset has operated in the past, but also I would say exploit the knowledge about physics and how the physics of the equipment works to be able to make them more meaningful. The whole idea is, I don't want to throw more false alarms at you. At the same time, I want to make sure I don't miss anything, right? So that balance is achieved by doing the kind of things I told you, and what we have done in our own thing. So we today cover propulsion systems, fuel systems, cooling systems, different kinds of propulsion, water jets, and so on, for different kinds of vessels. And of course, CBM has been applied, in my experience, to offshore assets, land-based, and marine assets. So let me talk quickly about another example, facet, I should say, of condition-based maintenance, which is the whole idea of AI for reliability and availability. So how do we do that? So the whole idea here is to be able to use artificial intelligence on the discrete data that we talked about, right? So when we look at it, there are 4 fundamental questions I want data to tell me, your transactional information to tell me. which is, can I benchmark my reliability of my major systems? What is my current baseline reliability looking at the last few years? More importantly, can I identify emergent risks in reliability, right? So things which are not yet become big, but the way that the reliability is moving, it may be a cause for concern in the future. And that is like a leading indicator versus knowing just the baseline reliability is very important as a lagging indicator. So you can, the point I'm trying to make here is you can use reliability insights to actually extract both leading and lagging indicators. Um, Reliability trends over time, which is to know which systems are actually moving such that I can expect what failure modes will come in the future, and I can plan against them. And then quantify the relative risk in reliability with multiple assets. So for example, if I have a fleet of vessels, a fleet of drilling rigs, a fleet of offshore assets and so on, can I understand and benchmark them on a fleet comparison basis to know where my entitlement risks are, or which part of my fleet has lower or higher risks on an apple to apple comparison. And that actually gives a lot of insight as to what is happening where. Okay, moving on to the next part is, of course, the how. We'll not talk about that today. This is about, the kinds of models that we have to build, statistical model, whether it's looking at basic viable modeling or look at more advanced modeling of failures, homogeneous poison processes, non-homogeneous poison processes to look at the inter-arrival rates and so on, and then quantifying that risk in a manner that can be understood, to be able to answer questions such as, do I need to improve my people or product or process? Answering questions like, for example, I've shown here on a example where I have different kinds of failure modes, right? Vibration issues, software issues, and so on across multiple vessels. And I can now start to understand why do I, or maybe I should say, we can now start to question, why do we have more mechanical failures in certain part of my fleet? Why do I have more software issues or vibration issues on a certain part of my fleet? And that becomes much clearer when we start combining this with the modeling of reliability risk, starting with understanding my bad actors. And this is all derived from data. So the whole idea is to remove the bias of what I or you may think are my top issues. Of course, that can be an input, but taking a look back, taking a step back to take a broader view as to what's happening. Moving forward, here is a analytics framework that I've developed as part of our experience. So obviously, it starts with data ingestion and data collection. Like I said, data ingestion is, well, how do I get data off my asset? How does it communicate to the cloud? How does it come back to the offshore or the central location? Where does computation happen? Is it edge-based? Is it central-based? So on. Data annotation is, well, do I understand what this data is? Equipment taxonomies, sensor mappings, and so on. And then the context of the data, meaning understanding how and where was this asset being operated. We then move on to stage 2, which is understanding and improving the quality of that data. We talked about that, and processing of this information to then start building asset health models. So if you see, almost half of the screen is dedicated to how we collect, what we collect, how we improve, pre-process, munge, clean, and improve data before any modeling can start. If you skip this, you may get some early yes, models. You can build some models, but they will not be very meaningful. And the kinds of models we built are reliability information models that we talked about, anomaly detection models, risk decisioning models. We touched upon those to basically derive insights about diagnostics and predictive management and inputs, so that they become, like I said, data-driven decision support framework. A key part of course, this leads to all the nice KPIs we talked about. A key part of all of this exercise is, if you see here, there has to be validation and feedback that needs to come back, and that is, I would say, one of the very critical elements, because that is how you continue to adapt your models. You can, no model is accurate on day one. So how do we continuously improve them? That's the whole point of machine learning, is continuous improvement. And then how do we make sure that the models remain current with the current emerging conditions and failures that are happening, or change in operating profiles? Okay. Let me quickly move on to the topic of digital twins. So again, widely discussed and printed topic. What is decision support? What is a digital twin and what it is not? Again, I think it's a very simply put, it's a faithful representation of the actual asset and the operations that it is doing onto a digital world or onto software. It basically, the main purpose for heavy assets is to provide you, the user, with the ability to perform what if scenarios at a low cost. So you don't have to go and change anything in the real asset. You can do it on a computer. Changes related to upgrades and modifications and controls and so on. Understand the impact of that change in these operating parameters in a digital compared to a real world. So you're much faster, cheaper, efficient. I should not say cheaper, it's cost efficient because it will take some effort to even build a twin. But overall, you can do a lot more experimentation with what you want to achieve and understand their impact than having to do it in the real world. So key concepts that I've seen, which basically, before this, let me talk about the dimensions. So I think for industrial assets or for power assets, marine assets, offshore assets, I think the three critical dimensions on which we should build a digital twin. And one is the operate cycle, which is digital twin, which basically is a faithful representation of how the asset is operating, maintenance, what, where, when, why would be required. It gives you operational transparency and optimize how your operations are done. The second bigger dimension is design, which is, of course, before operation. But there you talk about changing, let's say, softwares and with newer design upgrades, or how will the asset react if I were to change a certain type of a certain design or a fuel condition or a software control and so on. And then services, which is, which talks about various other dimensions such as inventory, parts, type of parts, and so on. I arranged them deliberately in a circle because these three dimensions are not in a silo. They're actually a lot of exchange of data and information and modeling insights happening from one to the other. You may choose if your organization wants, let's say, more interested in operational transparency or maintenance anomalies and so on. But at the same time, the model will still require inputs or at least the data to be able to build models related to the other two aspects and so on, right? The key problems I've seen, or I should say key things you should keep in mind when building a twin, are balancing the relevancy of this faithfulness between the physical and the computer representation. So there are two aspects to it. One is how faithfully and closely does your digital asset or your digital model, think of it as a model, right? So twin is ultimately a bunch of software. So how closely does your software actually replicate or represent what is actually in the fleet, in terms of configuration, in terms of design, and so on? How soon or how latent are you able to maintain that data between the physical and, so for example, you did a change in the physical world. How quickly does that start reflecting in your digital model, right? So if your digital model is still working on something, on information which is a couple of months old, the digital twin is basically obsolete, right? So you have to ensure that the latency is minimized. And then how do you maintain your model over time, right? So how do you account for swaps in the field? How do you account for services that are done, parts that are changed, human maintenance that is performed, and so on? And then, of course, there can be an uncertainty to a lot of factors, like not all crew will be able to update your model as quickly, and so on. So there's a lot of uncertainty due to that, and the economic factors, meaning change and shift of how and where this equipment is operated, right? So these are kind of things that you will have to look for here. Moving on, key lessons learned is basically one, like I said, several places during the whole idea of AI-based CBM is it's for your, meaning the user or the fleet owner or the crew engineer, your assistance. It is not to replace. Key lessons learned I've divided into several buckets again. So one is lessons learned in the data acquisition phase, which is, what kind of resolution will you need? Depends on what kind of problems you're going to solve, depends on what kind of sensors do you have. Connectivity, again, leading to how will your data get, is it batch mode? Is it continuous mode? Will you do computations at the edge versus at a central location? Data quality, again, we talked a lot about that. So key here is data quality has to be context-based, right? You cannot apply data quality from a field which is not related to the asset you're working on, right? So basically, it's not one size fits all. You have to develop data quality rules for the particular type of assets that you are looking for, right? Choice of methods. So those of you who have experience in modeling, different data types, how do I choose between the right bias and variance? Dilemma, how do I solve model complexity? A big problem is model maintainability and model explainability, right? So if I give you a black box model, nobody will trust it. I will have to break down the output such that it kind of makes sense from a user's perspective, from a physics perspective. And then similarly, if I have to maintain a model and it takes basically months to do that, again, you have to optimize the maintainability and explainability for the decisions you're trying to make. What kind of platform choices do you make, right? Consumption of how does the consumption, where does the consumption of the insight happen? How do you orchestrate the data coming and these models running? And then, of course, the human machine interface and the UX for taking PHM decisions and so on. And at the end, it's more importantly, the challenges in terms of lessons are also related to the adoption. So some things I've found useful as a lesson learned is, user training. Many times data scientists may fall into the trap, having one of them, that, if you build a model and throw it to the user, it'll get adoption. It doesn't happen. You have to work with the user for them to be able to trust what you're building. Every model has a shelf life. So you have to be cognizant of the fact models will also evolve as physical fields are evolving and as your asset is changing over life. How do we drive credibility? So I talked about various things here. User fatigue. So you have to optimize and specify upfront what is the level of risk that we are willing to take. Otherwise, the easiest option is to call everything an alert, right? And that will drive the user to switch off. So how do we minimize this user fatigue? And then, of course, continuous feedback to improve the models. So these are some of the lessons that we have learned. At the end, I'll wrap up with saying, of course, this is the same slide you saw earlier. I'm just talking about what is ABS and what do we do, and we talked about various services, and I think that's the end. So happy for questions and any email. My email is here. You can always email me for anything you may have. Rajneesh, back to you.
Hey, Subrat. Thank you so much. That was fantastic, and it was also very fascinating, very educational for all of us. We have a few questions, but before we go there, I just want to say that it is remarkable how you are able to ingest such vast volumes of information. I'm sure it's not just you; it's all the algorithm models that you put in place.
Yes.
But I definitely don't envy your job, because it's so much information to digest and to deal with. It's a universe out there, and it's really fascinating. So
yes,
it was great understanding this concept in detail. So a couple of questions. Let me start with the first one. The first question is, how long does it take for you or ABS, or for anyone for that matter, to build such an AI machine learning system for any piece of equipment? Say, is it like equipment specific, or is it for a full unit, like for an entire facility or a platform or a vessel? How do you kind of suggest people go about this? Small parts, take small parts and build it up, or just go one big thing? I mean, of course, I don't think it's possible to go complete one big unit. So just wanted your thoughts on how to implement something like this.
For sure. I think that's a fantastic question. So why I say that is because, this is exactly the type of challenge which many organizations have faced. My assessment in that regard is, number one, you should first take a look at, what are your biggest problems to solve. So for example, propulsion may be a big issue, or maybe a certain part of the process is a big issue. Then take a stab at, there are several ways you can try to prioritize, right? What will give me the maximum return on investment? What is my most, quote unquote, low hanging fruit? Because now it is easy to say low hanging fruit, but what I've found is you need to be able to first figure out, of course, what are your key problem areas? It could be your asset performance, it could be a certain type of components, it could be unplanned failures, it could be availability improvement, and so on. But then, do you have the data around it? Do you have historical information? Do you have sensors, and or maybe have you collected repair logs and so on? And then you would start looking at into kind of, so what I've found very useful is, first you should always do, again, not always set in stone, but a right way, one of the ways to look at it is start with performing a reliability assessment to tell you what are your bad actors, where you need to focus in terms of components and systems and failures. And then from there, make a mapping into where you have sensors available so you can connect these dots, right? So you don't want to start sensor analysis on something that may or may not have a big value for you in terms of frequency or impact of a failure. You want to start with a good understanding of both the frequency and severity, as we call in the actuarial world, of where my most failures have happened or where have my most unplanned downtime come from. It may not be a component, it could be a process, or it could be something else, right? And then you start building models, and that's the approach that I've taken, where we started by, and it's never one or the other. It's usually an iterative process. But I've actually started by looking at the reliability and identifying the bad actors and top failures, issues, and so on, moving on to sensors. And then, of course, sometimes you have to go back because you may have something that may be occurring a lot of times, but it's only a $10 component, right? So not big impact.
So, Subrat, you mentioned sensors. Now, do you kind of plug into sensors at the system level? Like, I've heard about things like APIs, they call them, application program interfaces. Is it kind of connecting to, like, for example, on an LNG carrier, we would have the automation system, IIS. So does it connect to that and kind of dump all the data from there? Do you take it from a VDR system kind of thing? What are the tapping points for this? Or do you go at the component level?
So we actually go at the lowest component level, because that's where you will get the sensors you need, right? We can ingest data today from the SCADA systems, or if sometimes the customers are pulling it to their central warehouses, we can pull from there. It can come as streamline or as batch modes.
Okay.
But usually it's OPC connections from SCADA systems that we can then start reading.
Okay, all right. Another question, like, is there a real life demo of this? Is it possible to kind of view this? We talked about digital twins and so many other aspects to this. Is there kind of a working model, maybe something which is very basic and not proprietary to any customer, which our members could potentially view or see a demo of?
I mean, we can certainly arrange that. We can discuss that and define the scope. Sure.
Yeah, I think that'll be very, very fascinating, because all of this, like, is, we talk about, you mentioned the word data hairball. I like that analogy a lot. It just, when you think about all this data and the bits and bytes that come across, is just immense, and how do you kind of untangle all of that and actually get to the key issue without kind of losing your way in that? So that would be very interesting to kind of see it working, and even if it's a very basic rudimentary thing, at least that puts us into the first step for accepting this and maybe implementing it, because I'm sure the costs involved are quite a bit. So yeah, I mean, with respect to costs, I don't know if you guys have any indicative benchmark numbers on, like, saying, okay, for a system, it'll cost you about this much. Does it depend? I mean, this may be something which you may or may not want to talk about right now, but just wanted to kind of get a sense of, is there, what's the payback like for this? Like, if I invest X amount of dollars today, in how much time from experience of having implemented this would a person, operational team be able to see the payback on this? Is it like a year, 2 years, 6 years, just to get a sense, basically?
So again, specifics, I mean, we can leave for later, but yes, the framework is very simple, right? So if you're looking at a reliability type assessment, typically it takes us about, somewhere between 4 months to understand fully and be able to benchmark what is the reliability of a system, down from a system, looking at a system of systems approach to a component. Then you start building these sensors, and of course, the simplest example I've seen is, if I can save you one failure, hypothetically speaking, if you look at the different things that add up to the cost, right? Of course, the cost of the part and repair is one thing, but then the lost opportunity to use that asset, that I've seen has a multiple X payback on the cost of building this whole process, right? So that's how I would, we have seen it working best. In terms of sensor data analysis, also it's the same thing. It takes us from few months to basically build, of course, depending on the complexity and the type of sensors we have, we can actually come back and turn around on those as well. So sensor based is anomaly detection, life prediction, and so on.
Okay. Yeah. So
So
I have a
the long
question here.
answer. Go ahead.
Sorry,
No,
go ahead, Subrat.
Don't worry, I finished my point.
Yeah, okay. So, one of the things was, and I have a question here from one of the gentlemen who's attending. The question is basically, how will you integrate this and merge it and, work with your CPS system in the ABS NSC, nautical systems enterprise? Because I'm familiar with NSC. I don't know if the failure modes and those kind of things, I mean, if those are used, and if this interfaces with that, or is this a separate system completely independent?
So the system is just to what I just talked about is the processing of the data for generation of the insight. How does it get delivered to you? It can be through NS, it can be through direct integration into your own CMS system. Doesn't matter. But of course, we work closely with our friends in the nautical systems.
Okay. Have there been any installations that are up and running now, like implemented fully by ABS, or maybe globally elsewhere as well? I'm sure there are other providers and other companies pursuing similar things, right? So how
Yes.
many are there? Is there quite a few already? Just kind of
I don't have I can tell you about ABS. I may not have a global count, but yes, we have several fielded applications now for commercial but broadly and heavily into the government, US government arena.
Okay. And also wondering from an implementation point of view, is it like a copy paste function? Like, can you develop it for one unit and then apply it to the others, or does it have to be iteratively done for each unit, each component, each piece of kit
For
from
sure.
scratch?
Again, very good question. There's no right answer here. See, you have to remember two things. One is if you think let's say a turbine or an engine. So if you say an engine is an engine, there is some truth that we basically reuse some of the models that exist. But then you have to see every engine is a different engine, because the kind of sensors it may have, the kind of field of ambient conditions and where it is being operated will be very different from the other ones, right? So there's always that step of how do you transfer built models and knowledge repository into a new asset, and that is the whole idea of you have to make sure the sensors are the same. They could be tweaking to the models required. There generally is re-optimization of parameters for those systems, and so on. But of course, we don't have to start from scratch every time. That's what I'm seeing now. We're actually able to use our existing models and then optimize, tweak, customize them to the newer asset. If I have built a model on a 10-cylinder engine, but maybe the next one is a 20-cylinder engine, I cannot transfer the model, right? There has to be a phase of retraining and learning and optimization.
Right. No, I think that's a good point. Yeah. So, Subrat, we also talked about data quality, and the human element that goes into actually putting those comments in place, and the spelling errors and things like that, and the language issues and stuff like that. So I'm just wondering, has to solve this issue, what would be the best way? I mean, should you then make the data entry process very, very tight and rigorous, where they can only choose drop downs? Like in many areas that we use for form filling and things like that, it is kind of pretty controlled, right? You can't type any free text. You have to select from certain selections that are already there. So would that be the way to kind of limit this? It'll be a very extensive form for entering information, but at least it'll be tight. It'll be
Yes.
well reviewed in advance.
So I would say, see, filling a form which has set drop-down menus has its own advantages, but only for a limited extent, right? You want the human to be able to enter his observations, because those are the key to tell us, what is he observing. You cannot possibly have all scenarios and all types of failures and all permutations and combinations. Otherwise, the form will be like, it will be a project to do a form. And if they have to do 50 repair entries in a day on a vessel or an offshore asset, I can almost, be very certain the data quality will be even further down. But basic things like, for example, if you are working on an engine, you cannot have I'm just throwing an example here, but if I'm working on an engine, I would never see a microwave appear near it, right? So you can't make those obvious mistakes, right? Only for those purposes to select the hierarchy or the asset type, and maybe the area you're working on, forms are very good. So I think it should be a hybrid solution where you take the user so that they cannot do basic errors, but at the same time you have to give them the freedom to be able to express what they're observing. Unless, like I said, you will have to create a giant system with every permutation of and every combination of every failure system.
Right. Yeah.
Not going to happen.
Yeah, sure. Yeah, I mean, you'll need to allow them to enter their comments as well. So that's a good point. Yeah. So we have another question here. It says, have you used AI for safety efficiency of marine navigation, such as AI techniques for predicting, forecasting water levels, surface currents, weather, etc.? I think it's possible, but anyway, I'd like you to answer that.
It is certainly possible. I personally may not have worked on that use case, but again, with the use cases we have worked on, I mean, there should not be a big stretch.
Yeah, because I think there was a mention that you've used this also in inspections and marketing. So I would think that there will be application across the
risk-based inspections, and then marketing applications is more like how, where, what to market. So that was more of a marketing campaign application of AI, which I did long time ago.
Okay. All right, good. So I think that's it for questions from us. I would like to, Subrat, first of all, thanks a lot. This was very fascinating. And on behalf of the Institute and our members and the Gulf Coast branch, I would sincerely like to thank you for this informative, fascinating, and very educational presentation. We greatly and sincerely appreciate your time and effort, specifically for you stepping away from your commitments today to accommodate us. I know you are at Rice University undertaking some training, and it's great that you were able to step out from that to accommodate this. So really appreciate that. I also want to thank all our global viewers who were able to join us for this webinar today and for their comments and questions. A big thanks to all those behind the scenes who make such webinars possible. Thank you. Also to our viewers, if you need any further information on today's topic, please don't hesitate to contact Subrat or ABS or IMarEST directly. Before closing, I would like to also mention that the IMarEST does offer continuing professional development credits to members who attend these webinars. So if you did register and attend, a CPD certificate will be sent to you via email. We look forward to having you join us for our future webinars and events. So do have a great rest of the day. And with that, we conclude today's webinar. Thank you all. Thank you, Subrat. Thank you.
Bye.